Okay, all right. Let's quickly recap what we talked about last time. So we were talking about uh, applications in of ideas that we've seen in signal processing. What did we talk about specifically? What did we discuss last class? Right. So when in practice we always deal with finite duration time domain signals, XFN, uh, and the signal might be defined from 0 to n. Okay, and okay, this is a finite duration time domain signal. How is this related to things that we've discussed in terms of vectors, vector spaces, and all that? Right. We can think, since it's a finite set of numbers where the order matters, what value corresponds to what time, we can think of this as a vector from Rn or for Cn. Okay. That means this is Cn and this is my origin. My time domain signal is now a point in a high dimensional space represented by this vector. Then, right. So if I say my signal x of n takes on values minus 1, 2, 4, 3, 5, 102, whatever, and minus 3, that means my vector x takes on these values. Anytime I assign a value to my vector, that means I've implicitly assumed a basis. And what basis is the time domain signal represented in? That's always the standard basis. E1, E2, N. And what signals do these correspond to? The standard, the ith standard basis vector. What time domain signal does this correspond? Right? EI in particular. Right? But what that's the vector. What time domain signal does this correspond? Del what? Not n. Is it right? N minus I, is it? Plus 1. Okay, all right. Okay, and then we then talked about vectors from Cn, where every element of this are elements from are complex numbers. We'll not review complex numbers, but we'll only talk about some, yeah, a couple of things. The standard inner product in Cn. What is the standard inner product? If x and y belong to Cn, this is y, and what is this? It's not correct. Okay, all right. And then, well, what is the length of a vector now? If it's from the 2 norm. Huh? No, what do you mean by x square plus y? This is a, see, x is a vector from Cn now. What is this equal to? No, no, x is from Cn. No, you understand what I'm saying? X is a vector from Cn. It's not a single complex number. Sorry? No, I'm talking about the Euclidean norm, square of the Euclidean norm. Hey, hold on. I don't know why everybody keeps saying a square plus b square. A single complex number is a plus jb. I agree the modulus of this is, or square of this is But this x is a vector from Cn. That means each element is a complex number. This is a complex number, which could be a1 plus jb1. This could be another complex number, a2 plus jb2, and so on and so forth. What is the 2 norm of this? 2 norm of x, the vector x, if it's from Cn. Hey, it cannot be n, no? Okay, fine, hold on. If x and y, if x was from Rn, what was this equal to? Not 1. Any arbitrary vector. Okay. Square what? This is simply sum of, what is this equal to? So what is it here? You can verify that this is equal to 1 to n. You take the modulus of each complex number and square it. Okay. Okay. And then I mean, in the same line, you can think about what would be xp if x is from Cn. You can think about, I'll not discuss that, but you can think about what it might be equal to. Okay. And then, yeah. Well, okay, if you have a set of vectors u1, u2, un that form an orthonormal basis for Cn, when would this set form an orthonormal basis for Cn? Yeah. Right. Same thing as, yeah, okay. Then, well, we talked about matrices. We can talk about complex matrices where each entry is a complex number. And then the transpose of a matrix, the AH. And then we also talked about what are unitary matrices. Okay. One thing to notice is the standard basis E1, E2, En. This is the standard basis, right? Rn. This is also the standard basis for Cn. Okay. All right. And then what did we talk about? We talked about the Fourier basis, right? Fourier basis for Cn. What is the Fourier basis? No, what is the Fourier basis? What are, I mean, Fourier basis is a basis. That means it has n, a set of n vectors from Cn which form a linearly independent set. What are those vectors? If you're specifically talking about the Fourier basis. Yep. So these are vectors of the form e raised to what? Yeah. Well, these are vectors formed by time domain signals of this form. And And it turns out that if you have a finite duration signal of length n, there are only n sinusoids, where W0 is not W1, there is nothing more, and there is nothing in between. just these. Well, I should be correct. If you're only talking about finite duration signals, then this is correct. But if you're talking about infinitely long sequences, then you can have any frequency between 0 and 2 pi. Whereas if you're talking about finite duration signals, then these are enough. These n sinusoids are enough. Okay. Okay, and then now how do we now convert or represent our original time domain signal x of n in the Fourier basis? Well, these form the basis vectors. My x was represented in the standard basis. This is the representation x. How do I get the corresponding representation of x in the Fourier basis? Well, before that, the Fourier basis is an orthonormal basis, provided you divide each one by 10. Otherwise, it's an orthogonal basis, not orthonormal. If we divide each them by root n, then this forms an orthonormal basis. If that is the case, how do we find the representation of x in the Fourier basis? A, what is A? If you form a matrix F in whose columns are -1 and there is a 1 by root n here, then this is your DFT. What is your inverse DFT now? Okay. All right. And then we saw an example of a signal that had rhythmic component. And then when we decomposed or represented the time domain signal in the Fourier basis, it looked like, or at least the Fourier basis gave a nicer representation in the sense that, so we had a rhythmic signal like this. Not exactly like this, but something like this. This was of some length n. This was your x. And then when we found the representation of this in the Fourier basis, we got the representation xf, and that was also of length n. Okay. And this one, after we removed the mean, had a representation like this. Most of the values of the signal in xf, for example, if you simply wrote it down as a set of numbers, most of them had very low value, except for few of them that had large values. Okay. Well, for now, let's assume these small values are 0, and then you had a non-zero value here, and then non-zero value here, non-zero value. Everything else was 0. Okay. Whenever you have a vector, okay, whose elements are mostly 0, and only a few of them are non-zero, these are called as sparse vectors. Okay. Sparse vectors are nice because there is only a very small number of pieces of information in a sparse vector, and it gives you kind of a cleaner representation of the signal. Because now if I look at this, even though here I don't know what exactly is there in the signal, if I look at the Fourier decomposition, I can clearly see that there are these 4 frequent. The signal is primarily composed of these 4 frequency components. Okay, whereas the rest of it is all 0. So when in this particular signal, when we chose the Fourier basis, you got a sparse representation of your original signal, which in the original signal, if you looked at the individual values, all of them were some non-zero values. Okay, so this was not sparse at all. Whereas because the signal had a rhythmic nature and you chose the Fourier basis, you get a much nicer and cleaner representation. Okay, but it turns out that going from something not sparse to a sparse representation depends on the nature of the original signal and the basis that you choose. So what's essentially happened is that the signal that you had components that look very much like elements from your Fourier basis. That is why you have a sparse representation. If I had chosen a signal that did not have a lot of rhythmic components, for example, signal like this, okay, the blue or the red line, where the signal was, this is one of the signals, the other signal was like this. There isn't anything rhythmic here where it's going up and down regularly. And in fact, the signal seems to have a low value for most times, except for a short duration of time during this entire time record, where it's changing, otherwise flat with very low values. The Fourier basis is very good for signals that have rhythmic components that are spread out across time, and they have oscillations, or they're the trends in the time in signal seem to have these oscillations that go up and down. Okay, whereas if you had signals like this that are short-lived in time, they don't exist for all time. They only exist for short periods of time, and we often come across examples of signals like this. For these, if you do the Fourier representation, what you get is shown here, and this is not necessarily a sparse representation like here. Here, if you only had these four components, you get a good approximation of your original signal. Whereas here, it does not seem like you have a sparse representation. So it turns out the Fourier basis is not good for signals like this that are short-lived in time or that are transient. And the solution to this is then to choose your basis vectors that are short-lived in time, and you choose enough number of such signals such that it spans your entire your Cn, okay, and forms a basis, right? And that is essentially what leads us to the idea of wavelets. Okay? When you are interested in working with signals that might be short-lived in time, the Fourier basis is not a good basis. Or trying to represent those signals or understand those signals in terms of sinusoidal signals is not really a good idea. Uh, Wavelets which are whose basis functions, for example, if you're when we're talking about signals that are or a finite duration, wavelets turns out uh, they the basis vectors that you have in a wavelet basis are composed of basis vectors that are short-lived in time, that exist for only short durations of time. And now you could ask, okay, how short is short, right? It turns out the wavelet basis has different basis vectors that essentially cover different parts of your time axis, that allows you to represent a short duration of signal that occurs anywhere along time. Okay, a very popular and a very simple example of a wavelet basis is called the Haar wavelet, and it has a very nice or very simple structure. I've written down an example of um, a Haar wavelet basis when n is 8. Okay? There are 8 signals. Okay? The Haar wavelet is the 8 Haar wavelets form a basis. They cover Cn, and they also form an orthonormal basis. Okay? The very first uh, Haar basis is essentially like the Fourier basis. It's all one. Okay? So if you're talking about signal of some finite duration, the first Haar basis is all this. Okay? The second one, what you do is you take your entire time duration, divide it into halves, and then you make the first half plus 1, the next one minus 1. Okay, that's your second basis. Okay, and then your next two, you take this and you make this, and the rest of it is 0. Okay, and the next one is like this. So if this was of length n, this is n by 2, this is n by 4. So this is 0 here. This is n by 2, this is 3n by 4. And then you go down further, you take this region and then you split it into positive and negative, and then you split this into a positive and negative signal, positive and negative, positive and negative. That's what I've shown there. And if you can verify that each of this has a length 1 and they are orthogonal to each other. If you take the standard inner product between any of these two uh, signals, you get 0 if your indices don't match, if I is not equal to j. Okay. So that's essentially the plot of what I've shown there. So W8, the Haar wavelet for signals of length 8, W Hermitian into W8 is I. That means the columns, the basis vectors do form an orthonormal basis. And this W8 matrix now, so if you have a signal X, right, your Haar decomposition is now no different from the Fourier decomposition. You simply form a matrix W whose columns are formed by H0 to H7 or H1 to H8, depending on how you represent them. So if you H1, H2, Hn, and if you take the summation of this, then you get the corresponding representation of your signal in the Haar basis. Okay. Now, the signal that I showed you earlier, where the Fourier basis did not work very well, if you do the Haar decomposition, let's say we take the red signal, and then I do the Haar decomposition. So this is the original time domain signal. This is the second row is the representation of the same signal in the Haar basis, and what you find is all the Haar coefficients are 0 except for this one coefficient. That's because, I mean, of course, I cheated here. I chose my red signal to have a shape that was very similar to one of the Haar wavelets. So only one of the basis functions has a large non-zero value. The rest of it is all is very small because it's essentially just trying to fit noise in your data. Okay. And similarly, the difference between these, for example, if you remember in the Fourier case, the red and blue essentially have the same shape except they're shifted in time. Because Fourier does not really care about where you're located in time. All it cares about is, does the signal go up and down, okay, across all time. If you take the Fourier transform for both of these, or if you represent both these signals in the Fourier basis, the representation you get more or less looks similar. Whereas if you look at the Haar, right, there is a slight difference. For example, if I don't know what value this is, somewhere close to 8 or 9. So for the red signal, the non-zero coefficient occurs at 8, whereas for the blue signal, the non-zero coefficient occurs at 10. So the Haar wavelet here does show that there is a difference between these two signals. That's because the Haar, if you look at the basis functions, there are basis functions that look like this. Okay? That means this basis function picks up anything that occurs only in this time window, whereas this basis function will pick up anything that only occurs in this time window. And because you've chosen your Haar wavelet to be able to cover all time, it is able to pick out the differences between these two. Right? And of course, you get the most sparse representation here because all of it is 0 except for one coefficient. That again is because I chose the original time domain signals to match what the Haar wavelet does. Right? So that's essentially, and so that's basically to demonstrate that both Fourier analysis and wavelet analysis are not really different from each other. It's essentially us looking at the same time domain signal using the Fourier basis or some other basis like this, like the Haar basis. Now, if you talk about any other wavelet transform, then all you're changing is the basis in which you look at the signal, basis with which you represent the signal. Otherwise, the essential idea remains the same. Just to give you another example. So, in the previous case, the Haar wavelet gave a nice representation because I chose the signals to match one of the Haar basis functions. But let's say we had a signal like this, right? This is also time limited. It occurs for a short duration of time. It's like this. Now you take the Haar Now you take the Haar basis and you try to represent this signal in the Haar basis. Well, it's not as, it is still fairly sparse because most of these are 0, except now it says it's got a lot of lot of Haar coefficients which are not 0, okay? Which essentially means that you need all of these Haar wavelet or basis functions to reconstruct this original signal. And because that sinusoid does not really match any of your basis functions, that is why you need several of these to get that sinusoidal shape that you have. Which is to demonstrate that if you now have a signal which does not match any of your Haar wavelet basis functions, then you'd still get a non-sparse representation. So you can come up with a signal where the Haar wavelet is got non-zero values for all of its coefficients. Okay, so the basic idea that I'm trying to convey is you might have a signal X, time domain signal. Next one. Okay, so you have a time domain signal. Vast majority of what we do in signal processing is essentially to find the basis to represent this signal in. This is the time domain signal. Okay, choose a basis so that some features in this come out really nicely. Okay, when I say really nicely, we would ideally like to have notation. If you know something about this signal, and if there exists a basis for Cn, where some of the basis vectors have similarities to your original time domain signal, then you'd get a sparse representation. But if you don't choose your basis correctly, then you're essentially not getting anything useful, right? Essentially, this is like you have something that you're looking at. Let's say this is a time domain view. If you say you're looking at it from a different basis, then you're essentially moving around and then looking at it from another angle and trying to see, do I get a better view of, better understanding of what the signal represents? So it's very important that to get a meaningful view here, a representation here, that there is a good match between your X and your basis, right? It turns out that is very difficult to attain when you deal with, well, a basis set that only has, well, what is the definition of a basis? It's a linearly independent set. And how many elements does it have? And it let's say we're talking about basis for Cn, it has to be a linearly independent set, and it has to span Cn. And how many basis vectors will it have? It'll have n basis vectors, right? And we said, well, the nice thing about the basis is you can represent any vector from Cn uniquely using these basis vectors, right? Let's see, these are the basis vectors. If you have a basis for Cn, any vector x can be uniquely represented like this. If your goal is unique representation, then this is good. But if your goal is to get a simplified representation, okay, then it turns out that the basis itself is not really that useful. Okay, what is useful is you don't restrict yourself to a basis, but you look at what is called a over complete basis, which simply means, okay, this is again a set that has more elements than n. So let's say we have an over complete basis for Cn. Then you have U2, U1, U2, U1, and Um, where M is n. Okay. So if you want sparse representation like this, so the current trend is to look at over complete basis, which will give you a clean representation. Okay. This idea of over complete basis has a lot of, is very popular in signal processing and neuroscience as well. It turns out the brain also does something like this, where it uses over complete basis for representing things, at least in the visual cortex. The one issue here is what happens when you have more vectors than you need to span a space. So if I have a vector x from Cn, okay, and a set of vectors u1 to um, I put them in a matrix, and I want to find the representation of x in terms of these vectors. Let's say I'll call this vector b. I want to find the representation of this vector b in terms of these m vectors, and m is larger than n. What is the problem here? And what we want is we want to solve for this x. Right? There are infinite number of possible x's that can represent b. Okay, but it turns out that, so of course, if there are infinitely many, then you have to have a criteria for choosing what is best for you. So it turns out problems like this are very useful when dealing with, I mean, when you're dealing with over complete bases, you're dealing with problems like this, and you solve this again through some optimization procedure, where you say, give me a solution for this such that x is maximally sparse. That means I want most of the elements in my x vector to be 0, such that if I take this matrix and multiply it by x, I get b. Okay, so we'll look at some of these when we cover optimization in the second half of the course. Okay, well, with that, I'll stop here. That's all I wanted to say about signal processing. If there are any questions now about matrix inverses and what we've covered now, we can discuss it before we move on to the next topic. Yeah. Yes.
If the basis of sigma matches with the basis of the Fourier basis.
Oh, no, that's not what I'm saying. Okay. Imagine you have, again, we're dealing with Cn, and you have a basis u1, u2, um. Okay. I put this down in a matrix form. Okay. And I ask you, what is the representation of u1? This is in the standard basis, in the u basis. Okay, what will happen? So, okay, this is your u matrix x. No, sorry. X is what is not known. X is your unknown. You want to represent u1 in the u basis. Okay, x is the representation of u1 in the u basis. I'm asking you, what will be x? Sure, what will it be? Right, this is correct. So you do this. I'm asking you, what will be the elements of x? Okay, maybe we do a simple example. Say u1. Let's keep it well. Sorry. Okay, this is my basis for R2. Asking you, well, this is equal to, what is the solution for x? Here, this vector, the way I've written this is essentially ax equals b. I'm saying u1 is in the standard basis. u1 and u2 form a basis for. I want a representation for u1 in the u basis. Well, you'd say, well, x is u inverse u1. I'm asking you what is, so I've given you numbers. Can you work out what is x1 and x2? You essentially have to solve this linear equation and solve for x1 and x2 and tell me what you get. Okay. What do you get? But what is 1, 0 in R2? What kind of a vector is this? No, no, no. There is a name for this. It's okay. All right. What if this was equal to u2? Instead of u1, what if I wanted to solve this for u2? So if you solve, so well, I'll call it x. I'll call this x1. Isn't that strange? Which basically says the representation of u1 in the u basis is e1. Okay. Or look at it another way. Is this representation sparse? It is. Well, there are two possibilities. One of them is 0. So this is a sparse representation. And in fact, it says of u1 in the u basis is 1 for the first basis vector and none of the second basis vector. And that happened because you chose your right hand side to be one of the basis vectors. The representation of u in this is just take u and leave the rest of them. Okay. So this idea of sparsity comes in when you have, let's say you have a lot of column vectors and you want to represent some vector b, x. If b exactly matches one of these, right, then the solution for this will be ei, assuming it matches with the ith column here. It does not match exactly. Let's say this is a combination. This is alpha 1, alpha times b3, or let's say this is a1, a2, am. Well, let me call it an. It's a square matrix. If it was like this, if you solve for this, what you would get would be a vector where everything is 0 except for the third component, third element, that will be alpha 3, and the 17th element will be alpha 17. Everything else will be 0. That happened because this b had exactly alpha 3 times b3 here, or sorry, it should be a3. I'm sorry, a. In alpha 4 times a17. Okay. So you get a sparse representation whenever this here matches one of these. But the problem is if you have more columns than number of rows, then there are infinitely many representations. Then you have to enforce sparsity, saying, give me an x that where the number of zeros are, which has the maximum number of zeros. Okay. So sparsity comes, I mean, your sparse representation comes out because your signal that you're trying to represent matches very well with one or a few of the basis vectors that you have. Yes, good question. Yes. The basis vectors are all in the standard basis. Okay. So for example, when we are dealing with ax equals b, and I can think of this equation as I'm trying to find the representation of b in the a basis, and the assumption is b is in the standard basis, and the a basis vectors are all represented in the standard basis. You see what I mean? Okay. And another way to understand this, as far as here, if you consider this problem, as far as the u basis is concerned, the first basis vector for the u basis is u1. So for anybody who's working in the u basis, their first basis vector is not 1, 1. Their first basis vector is in fact e1, because e1 is because for that person, this is his or her standard basis. The very first column, or very first basis vector for them is their standard basis vector. That's why the representation of u1 in the u basis is e1, because for the people working with the u basis, this is their reference. Okay, that is why when you solve this, you get e1. Okay. Yeah. Anything else? Okay. All right. Then we move on to the next topic. The next module is another important module, is on eigenvalues. Use n. It builds on things that we discussed when we talked about matrix inverses, where we were concerned with change of basis. Change of basis for representing vectors, right? Because this is how we start. That's how we started the discussion. Okay? So in this, we're going to look at something slightly different. Let's say we have a linear transformation f from Rp to Rp, or Rn to Rn. Okay, that means if I take a vector from Rn and I pass it to f, I'll get another vector y. This will also belong to Rn. And because we are dealing with a map from a finite dimensional space to a finite dimensional space, we can represent A, the function f, through a matrix A. Okay, so we can always find a matrix. And what will be the shape of this matrix? We can always find an n cross n matrix such that if you simply post multiply your vector x by A, you'll always get y, which will be equal to f of x. Okay, this we know. This is algebra. Let's say we're talking about R. And let's say our matrix is the algebra is okay, but I want to understand things geometrically. Okay, I could ask, okay, what is okay? If A represents a mapping from R2 to R2, that means it's taking a bunch of points here and transforming them in some way to produce points here. Okay, this is my output space. This is my x belongs here and y belongs there, or Ax belongs here. You're doing some sort of transformation of points here and taking them there. It turns out when you're talking about linear transformations, there are a few things that matrix multiplying a matrix, post multiplying a matrix by a vector does. Okay, it can scale the vector. Okay, it can rotate x, can also reflect. Can do these three things. Reflect x. Okay, so if I have an x here, if I have any arbitrary matrix A, I might get another vector y here. Okay, I can think of this transformation as, so let's say y is longer than x, as me having stretched this x vector and then rotated it to get here. That's one way of thinking about it. Or it could have done a reflection operation. Reflection is where it's as if you keep a mirror. So for example, if I want to reflect this vector about the y-axis, the corresponding reflection would be. So that operation is also right. So geometrically, what A is doing is essentially one of these, or a combination of all the three of these operations. Right. That's what is happening geometrically. Now, one way to understand what really is going on is instead of asking what happens to an arbitrary x when you do this transformation, you can ask what happens to the standard basis vectors. Okay, what happens to E1 and what happens to E2? And also another useful thing is you also consider this point. So essentially, you take a square, okay, located at the origin, where along E1 and E2, and ask what happens to the square. What happens to the square if you apply this transformation to this square? Essentially, I'm asking you essentially apply the transformation to these 4 points and tell me what happens. What happens when you apply the transformation to 0, 0? 0, 0, nothing. Linear transformation, 0 gets mapped to 0 always. Okay. What happens to E1? What will I get exactly? What is A times E1? What is it? 2, 1. Well, you're choosing 1, 0. That means you're choosing the first column, not the second column. That's 2, 1. Okay. So that's this point map here. What E2? 1. What's this? This is 1 minus 1. That's here. So let me, this is a circle. And we'll draw a square here. So dot gets mapped to a dot. This cross gets mapped to a cross. This triangle gets mapped here. What about the square? Hmm? Yeah, what do you get? Tell me where it will be. What is this point? No, no. What is this point? What is the 1, 1. So what will 1, 1 get mapped to? Well, just multiply. It will be 3, 0, right? So that is here. So the geometric operation this A is doing is it takes the square and then converts it into, well, not really a rectangle, but a parallelogram. Okay. What about a matrix like this? What will this do? Let's do the same thing here. What does this do? Zero gets mapped to 0. What about E1? That's here. What about E2? That's here. And 1, 1. So this is mapped here. This here. What about this point? It gets mapped to 3, 3. But it gets mapped to this. Well, I should not draw this, but yeah, it gets mapped to this. Okay. I just said a linear transformation does these 3 operations. Can you explain what's happened here using those 3 operations? Scale, rotate, or reflect. Well, you've stretched along this direction, and then you've squished along this direction, and you've rotated it. Okay. So you can explain this. So what about this matrix? Well, you squish everything to 0. Okay. All right. So it looks like linear transformations you can explain by these. Okay. And that is what is happening geometrically. Okay. Now let's, and again, uh, because I've put down numbers, okay, we've started with this, right? Okay. Now, let's take a vector x. Let's say, what is my y? For this one, you tell me what is y. This will be 2, 1, 1, 1, 1. Now this is 5, 1. All right. Now, I said a vector x and I put down numbers. That means I've assumed the basis. Okay. Let's assume this is in the standard basis. And this matrix A represents this geometric transformation, okay, that I've shown right here. Okay. Under that geometric transformation, if I take this vector 2, 1 represented in the standard basis, I get a vector 5, 1, and this is also in the standard basis. Okay. Now, let's say I don't want, I mean, maybe you like the standard basis, but I don't. I want to work with this weird basis V. Okay. I'll just write the matrix 1, 1, minus 1, 1. I want to work with this. The inverse of this matrix, you can work it out, but I'll just write it down. We can verify that this is in fact the inverse of this matrix. Okay. What is the representation of my x vector in the V basis? Okay, what is that? So you have to do V inverse x. What do you get? Can you tell me the number? Sorry. Okay, all right. See, both xv and x represent some point here, which is 2, 1, this point. Right? It's just that the standard basis basis represents it like this. The V basis represents it like this. Okay. But the geometric operation that we're doing, I mean, that does not depend on any the exact operation that I'm doing, stretching and squishing. That does not depend on any basis. Okay? So now, what would happen if you apply the geometric transformation A on this vector? What do you get? Can you tell me the number or tell me the vector? 4 is it? Outside. Okay, 1 by 2. Now, this should ideally be equal to that vector y represented in the y basis, right? Because A is just doing this geometric operation. That means this should be equal to yv, right? Representation of y in the v basis, because I've applied this geometric transformation to the representation of the vector x in the v basis. So if I do the same geometric operation, the person who's looking at that vector from the v basis should say, well, what I see is yv. But what is yv? How do you get yv? Well, I know y. How do I get yv, representation of y in the v basis? Okay. Well, this should be equal to this, right? You can verify. You will find that this is not equal to this. Okay. That means there is a problem. Okay. It looks like, I mean, we said, oh, we have all these different bases that we can look at stuff from. But you take a simple geometric transformation represented by this matrix. If two people are looking at the same thing from two different bases, and you do a geometric operation, the outputs that they get don't agree with each other. Okay. So there is a problem somewhere. And it turns out the problem is this. Like in the case of vectors, anytime you put numbers to stuff, I described this geometric operation and then I said, okay, these are the numbers that represent this geometric operation. It turns out that anytime you want to represent geometric operation in terms of numbers, you again have to specify what basis. Because here, you can think of a matrix A as a bunch of columns, A1, A2. The moment I put numbers to these vectors, I have to tell you what basis it is in. Okay. Here, we implicitly assume everything was in the standard basis. So if I take E1, I said it becomes 2, 1. That means it becomes 2, 1 in the standard basis, not any other basis. Similarly, E2 becomes whatever it becomes, 1 minus 1 in the standard basis. Means this A here, you cannot simply take a matrix and use it. You have to make sure that it also represents the geometric operation you're interested in the same basis from which your vectors come from. Okay, so matrices are representation of linear transformations. Representation of linear transformations are basically, right? And this A that I've drawn here, this is the representation of this stretching and rotating operation in the standard basis. That means you can use this to carry out this operation only if your vectors come from the standard basis. Okay, all right. Okay, I want to know what this is in the V basis. Okay, how would we figure that out? Well, I wiped it. It's fine. Well, let's see if this works. Okay, all I know is that my A represents some geometric operation in the standard basis. That means if I have my A, if this is in the standard basis, you always think of it like this. Whatever comes to the left has to be in the standard basis. If you put anything else, what comes out might not make any sense. What comes out is in the standard basis. Okay, that means what to have this A represent this geometric operation, you have to put stuff in the standard basis and interpret what comes out in the standard basis. Let's say I have xv, I don't have my representation in the standard representation of that x in the standard basis. And I have A, which is this is in the V basis, but this is in the standard basis. What can I do? But I know my V basis, right? I know V and V inverse. Well, I can take this. I know this in the V basis. I convert it to the standard basis. How do I convert this to the standard basis? V or V inverse? No, that was a trick question. It's V. Okay. So if you do this multiplication, what comes out here is in the standard basis. Okay. So this is okay. So whatever because this is equal to x. Okay. But what we are interested in is this. But what comes out is in the standard basis. What we want is in the U base. We convert what comes to the
V inverse.
then you do V inverse. Okay. So if you have V and V inverse and the geometric transformation that you're interested in, or the linear transformation that you're interested in the standard basis, and if you want to work only in the V basis, then all you have to do is you take vectors from V in the V basis, convert it to the standard basis, apply the transformation, and convert back to the V basis. Or equivalently, this whole thing now, the product matrices is AV, or the representation of this geometric transformation in the V basis. Is that clear? Here, this one matrix represents the same geometric transformation in the V basis. What is happening inside? This is essentially the product of these three. There is a V first, which converts things and here, because this is representation of the same geometric transformation in the V basis. What comes in here has to be in the V basis, and what comes out here has to be in the V basis. Okay? And if and the relationship between this geometric transformation in the V basis and the standard basis are these two are dependent on these two matrices, V and V inverse. Okay, and this type of a transformation where you have two matrices A and B, okay? You have two matrices A and B, the square matrices, right? And A and B are related like this. Okay, well, because I've written Q inverse, that means this is an invertible matrix. Okay, and these have to be n cross n because A and B are n cross n. If you have two matrices that can be written like this, okay, then A and B are called similar matrices. They're similar because they represent the same geometric operation, but in two different bases. But now you have to tell me in which basis. For example, if I can write A like this, and I say both of them represent the same um, geometric transformation, one in the standard basis and one in the Q basis, because I've written matrix as Q. Which of these two matrices represents this geometric transformation in the standard basis? Right. B is the representation of the geometric transformation in the standard basis, and A is in the or the Q basis. Okay, and this type of a transformation is called a similarity transform. Okay? Like I said in the last class, whenever you see an A inverse or some matrix inverse, you can think of at least, let's say it's a long formula and you see A inverse in the middle. One possible interpretation of what is going on here is whatever comes in here, if that comes in the standard basis, you are transforming that into the A basis. And whenever you see stuff like this, where you have a matrix in the middle, Q and Q inverse on the other side, that means you are essentially converting the geometric operation represented by B to the Q basis. Yeah, okay, all right. And you can verify that, in fact, that if you do this, you'll get YV and YV that you calculate, or if you compute AV multiplied by XV, you will get YV, which will be equal to Y inverse of, or V inverse of Y. Right. So that first part was essentially to convey the idea that not only are representation of vectors dependent on a basis, linear transformations represented by matrices also depend on the basis of choice. Okay? If for example, if you're talking about working in the Q basis, if Q and Q inverse allow you to switch between the Q basis and the standard basis, something like a similarity transformation would allow you to translate linear transformations from the standard basis to the Q basis. All right. Now that is just some basic information to the module. Okay. Now we come to this idea of eigenvectors and eigenvalues. Let's say we have a matrix A that is n cross n. Okay. It turns out linear transformations of this, in fact, let's say Cn. It turns out all linear transformations of this form, well, I said they do three things, right? What do? They scale, they rotate, and they can also reflect. Okay. So if you give any general vector as if you take any vector x and multiply it by a, it'll do all these three operations. But it turns out that there are these special vectors from Cn such that if you take a and you multiply, if you take that vector and multiply it by a, what comes out is essentially this, where, well, x belongs to Cn and your lambda is simply a complex number. That means there are these vectors in your Cn, for example. this is your Cn. There are these vectors x. There is, or at least there is at least this one vector x, such that if you take the vector and multiply, post multiply the matrix A by that vector, what comes out is simply lambda times x. That means the vector does not get rotated; it only gets, okay. And this is again a fact about linear transformations. All linear transformations will have at least one vector like this, okay. And vectors like this, who, when you apply this linear transformation and they don't undergo any rotation, they only get scaled. These are called eigenvectors. Okay. Or in this case, you, if x satisfies this, then you say x is an eigenvector of A, and the corresponding lambda here, which is a scalar, is the eigenvalue of, or eigenvalue associated with x. Okay, and you have to notice one funny thing here. If you take, if ax equals lambda x, right? If I take alpha times, if what I will get will be lambda times alpha times x. Okay, so there are infinitely many x's you can choose from, such that ax equals lambda x, where the lambda is fixed. For example, if I have an x where this is 2x, if I take 4 times x and multiply it by a, what I will get will be 2 times 4 times of x. Okay, so what matters is this eigenvector is this vector from the subspace spanned by x. Okay, so for example, here if I choose any vector along this subspace spanned by x, ax will give me lambda x. Okay, and the lambda is fixed irrespective of what size I choose x. If I multiply by a, what comes out is lambda times whatever original vector. Okay. And the reason this, so this term again, it's a German word, supposed to mean characteristic. It turns out that these vectors and this and these scalars tell you something inherent about this matrix. Okay, that is why it's called eigenvector and eigenvalue. Eigen simply means characteristics, or it could also be self, I think, or something like that. Okay, see, you could ask, okay, why is this ever? The very first time you come across it, the first question that comes to your mind is, why is this even relevant? Why should we bother with this? It turns out this is important because it's very helpful in dealing with stuff like this. We'll discuss things like this in the next lecture, but I'll just give you an example. Okay. These are representations of linear dynamical systems. Okay. Continuous time and discrete time. Okay. It turns out the solution to equations like this, where you say you have a vector x, the rate, and you have this strange looking equation where you say the rate of change of that vector x depends on, but multiplied by some matrix A. Okay, this is very similar to things you might have seen in high school, where you say rate of change of x is 5 times x, and you're supposed to solve something like this. This is simply the generalization of this, except now instead of a scalar here, we have a vector, and the rate of change of the vector depends on another vector, which is ax. Okay. And we are doing saying the same thing here. The next value of this vector, the value of this vector at the time instant n plus 1 depends on the current value modified by this matrix A. These turns out these are very useful. Okay, and the solution to this depend very much on this lambda and your eigenvalue and your eigenvector. Okay, for example, let's say Now, one thing I should notice is these are functions of time. Okay. Again, maybe that's that's a new notation where we've always written vectors or n vectors as set of numbers. Whenever you see something like this, where it is a function of time, what we mean is every element here is now a function of time. So this will be x1 of t, x2 of t, xn of t. That means depending on the value of time, the value of this vector itself changes. Okay. Now, turns out that if you choose your x of t, let's say lambda 0 and x naught are, or let's say x naught is an eigenvector of A and lambda naught is the eigenvalue corresponding to x naught. If you choose a solution to be like this, x naught multiplied by e power lambda naught t. If you take the derivative of this is a fixed, remember this is a fixed vector. If you take the derivative of this and you get x naught, what is the derivative of e power lambda naught t with respect to time? It's lambda naught multiplied by naught t. Okay. This is the left hand side. This is, what about ax? We've assumed x of t to be so. This will this be. This is a times x naught e power lambda naught t. But x naught is an eigenvector of A with lambda naught as its stated eigenvalue. That means this is nothing but lambda naught times x naught e power of t, and this is equal to this. Right? So in fact, functions of this form are solutions to equations like that's areas where eigenvalue vectors are very useful. That means any general solution that you come up with will simply depend on your eigenvalues and your eigenvectors. And you can show the same thing to be true in this case as well, except the solution here will be of the form x of n equals x0 lambda naught power n. Okay, this is where it's extremely useful, eigenvalues and eigenvectors. Okay. See, then the question is, okay, given you an example of where this might be useful, then the question is, how do we find out the eigenvalue and the eigenvector? So if you have a matrix A, it's equal to x. Let's say x is an eigenvector and lambda is the associated eigenvalue. If you move things around, then you get A x minus lambda x equals 0, 0 vector. I can take x out. In fact, you can verify this. You can write it like this. This whole thing can be expressed like this. Some matrix A minus lambda I multiplied by x is 0. Okay. And again, I should notice one thing. If you choose x to be 0, this will be trivially true with eigenvalue 0. So here x is not equal to 0. So you cannot simply put 0 and say, oh, 0 and the 0 vector are eigenvalues and eigenvectors of this matrix A. And before I forget, a lambda and x, where x is an eigenvector and lambda is the eigenvalue associated with, is called an eigenpair. Okay. So what we're saying here is if you take the matrix A and adjust this matrix by some eigenvalue multiplied by I, then this matrix multiplied by some non-vector x, and which is the eigenvector, gives me 0. That means this matrix now has a null space. Okay? Because when I multiply this matrix by some non-zero vector, I get 0. Right? And this eigenvector is in the null space of this matrix. Now the question is, how do we solve for lambda now? To solve this, the standard procedure is you simply take this matrix and find its determinant. Okay, we've not discussed determinant, but I'm going to rely on your prior knowledge of how you compute determinants. We'll do one example, and then maybe that's enough to at least get a handle on this. Let's say A is okay. We want to find the eigenvalues and eigenvectors of this. First, you take A, subtract it by some lambda times I, and find its determinant. Okay. What is A minus lambda I? So that's simply 3, 1, 1, 3 minus lambda I is simply lambda 0, 0 lambda. Well, we are still interested in finding the determinant of this. So that means I'm interested in determinant of lambda 1, 1, because 1 minus 0, 1 minus 0. Okay. What is the determinant of a 2 cross 2 matrix? It's the product of these two terms minus the product of these two. That is lambda square minus 1. This will be 9 minus 6 lambda plus lambda square minus 1. That give me lambda square minus 6 lambda plus 8. And you solve for this by equating this to 0. Okay. You simply solve for the roots of this, and then you get two values. You get 4, 2. Okay. So these are the two possible or two eigenvalues for this matrix. Okay. That's because if you choose lambda to be 4 in this expression, A minus lambda I will become singular. If you choose lambda to be 2, A minus I lambda will become singular, which is equivalent to saying determinant is 0. Okay. Right. So now that we know the eigenvalues, we need to find the corresponding eigenvectors. Okay. And the way you do that is you go back to the original expression. Here, if I substitute 4 here and I find out A minus 4i, that multiplied by the corresponding eigenvector should give me 0. Let's say we choose lambda equals 4. This is 1, 1, 3. And then I choose 4 first. So this is 4, 0, 0, 4. This whole thing multiplied by the corresponding eigenvector should give me, what is this matrix? And this vector is simply x1, x2. Needs to be more serious. What is this? So this will be minus 1, 1, 1 minus 1. So what is x1, x2? What is this equal to? So that I get 0. Well, if I choose 1, 1, that will give me 0. Right? So looks like for the eigenvalue lambda equals 4, the eigenvector is x. You don't have to trust this. We can verify if this is correct. How will you verify if this is in fact this is in fact an eigenvector of A with eigenvalue 4? How will you verify? Well, you substitute this. Find out if A times 1, 1 is 4, 4. So 3, 1, 1, 3. If you say this is an eigenvector, then this is equal to 4, 4. That is 4 times 1, 1. It's in fact correct. This is in so 4 and 1, 1 form an eigenpair of this A. Okay. Can you tell me what the eigenvector is for lambda equals 2? Using the same procedure. You do A minus 2i into x is 0, and then you find out x. So for this matrix 3, 1, 1, 3, the corresponding eigenpairs are 4 and 1, 1 and 2. This is for a 2 cross 2 matrix. And for a 2 cross 2 matrix, we got two eigenvalues. And at least in this particular case, we got two corresponding eigenvectors. Okay. Now, if you take a general n cross n matrix, you do the same thing. To find the eigenvalues, you take the determinant of a minus lambda I n and equate it to 0. Compute the determinant, you okay, some p of lambda equated to 0 and find the roots. This will, if it's an n cross n matrix, this will be an nth order polynomial. Okay. If you have an nth order polynomial, how many roots does the nth order polynomial have? It has n roots. And allowing complex numbers, okay? It can have n roots. That means an n cross n matrix will have n eigenvalues. It's just that the eigenvalues can be repeated. Okay, it can have, if you're talking about here, in this case, we could have come up with a matrix where both the eigenvalues were, say, 2. Because we only have 5 minutes, we will not proceed. We'll maybe do another example for finding out the eigenvalue and eigenvectors before we proceed. And then we can take it up from next class. What if A was, what are the eigenvalues and eigenvectors of this matrix? Eigenvalues? Only one, is it? Uh, well, as I said, in this case, it's repeated. What are the eigenvectors? Well, what happens when you do A minus lambda I or lambda A? So you get this. Exactly. Any vector is an eigenvector in this case, and it gets scaled by 1. Okay. What if I did this? Now you tell me. Okay. 2 and 3. What are the corresponding eigenvectors? One zero here, is it? Or here? Here? For eigenvalue 3? 0, 1. And what do you get when you do? What do you get when you do A minus 2i? Right? So what does x have to be for it to be 0, for this product to be 0? Well, the first value has to be 0. The rest next can be anything. So for 2, it's, let's just choose 1. What about here? 1, 0. The eigenvectors are simply the standard, the unit vectors with eigenvalues to nth. Okay, all right. Yeah. Now, right. Now, if you have an n cross n matrix, you will have n eigenvalues. Okay, it can be repeated. And uh, you will have, or you can have n eigenvectors. Okay. But one thing is to be noted. if you have two eigenvalues that are not equal to each other, okay, their eigenvectors will be distinct. X1 will not be equal. That's one thing to remember. I said where eigenvalue and eigenvectors are useful. I'll simply introduce the idea now and then we'll discuss this next class. This idea of looking at the eigenvalues and eigenvectors also has a useful application in simply find linear transformations. For example, if you had a matrix like this that does some linear transformation, this here some reflection and or rotation or reflection and scaling. What does this do? Well, there is no simple answer. You can think of it two ways. It simply stretches the x component by a factor 3, the y component by a factor 2. Okay. And you'd say that this matrix is a lot simpler than this, right? Because if, for example, if you had ax equals b, and if this was diagonal, there is actually a simpler version for the equation than diagonal matrix. Because if A was diagonal, then let's say A was like this, d1, d2, dn, right? Then this equation that you have here goes from a set of simultaneous linear equations to a set of decoupled linear equations. Because if this was diagonal, then d1 times x1 is b1, d2 times x2 is b2. So there is no relationship between them. You can solve them all independently. Okay? So diagonal matrices do simplify things because they remove coupling between things. Okay? Because, okay, we said, well, representation of geometric transformations are basis dependent. You could ask a question, okay, are there bases? For example, remember when we talked about sparse representation, we asked if you have a vector x, is there a basis in which the vector looks very sparse? Okay, we can ask something similar here for linear transformation. We can ask, is there a basis where this complex or this what looks like complicated to me, this complicated representation for a linear transformation has the simplest possible representation, and the simplest possible is a diagonal representation. So we are essentially asking a question, is there a similarity transformation that makes my matrix A looks like a diagonal matrix? And it turns out that similarity transformation involves the eigenvectors. Okay. Yeah. And then we'll do this up again on Monday. Are there any questions so far? Okay. All right. See you guys Monday.